In this video, we're going to go through the graphing skills, part 2. So you did the graphing skills part 1, which was basic make graphs, and then answer questions about guessing about proportionalities and basic equations, interpolation and extrapolation. We're going to do 2 additional skills here. So buckle up, here we go. So I'm going to walk you through this packet, and at times I'm going to say, stop the video, do the thing, and then you'll come back and you'll see it done. So first, we've got the data below is collected by measuring the distance traveled by an object over a period of time. And so you have distance and time here. I would like you to make a distance versus time graph here. Stop your video, grab your pencils, and make that graph. All right, you're restarting the video. Oh my God, look, there's the graph. Let's talk about what we see here. We have our proper title. We have our distance on the vertical, time on the horizontal. We have a nice scale that uses as much of the axis as possible. Same thing here. We've got experimental points, and there you go. And that 0, 0 is an interpolated point, so it is uncircled there because, you know, in no time you don't do anything. So there you go. You'll notice here you can see the erasure. I did it in pencil and I screwed up the first time I was making my lovely, lovely curve. And so I erased it and tried again because I, once again, did it in pencil. All right, so here we go. What seems to be the relationship between time and distance here? Well, if I'm looking at this from our previous discussion, this looks like our squared relationship, right? It looks like a parabola. So let's write the proportionality for it. Remember, when you're writing a proportionality statement, we always start with the dependent variable. So in this case, it says to use d for distance, so distance. So distance is directly proportional. And now, since it's a squared relationship, we're going to express the thing on the horizontal axis and then do the operation to it. So distance is directly proportional to time squared. Right? Now it says here to write the equation. So I started with the proportionality, and if I want to turn this into an equation, remember what I do is I go d is equal to, I take out the proportionality symbol, put an equality, but then, because it's an equality now, I need to be able to, I can't plug into this. If I plug into this, I need to understand that there could be a constant there. So I'll put a constant there. D is equal to kt squared. All right, now next is the distance between 0 and 1 or 3 and 4 greater. Well, we can look at this. Between 0 and 1, it travels a total of 3 meters. And from, 3 to 4, it travels many more, 21 meters. So there you go. Next, what's happening to the slope of the line as the time increases? All right, so there's going to be a tendency, well, answer this for yourself. There you go. There's going to be a tendency to want to say the slope increases. Now, that is a correct answer here, but I would rather you said that the slope got steeper, because the slope getting steeper is descriptive for what's happening to the slope of that line. It increases because the value of the slope is going from 0 towards a large positive number. Remember, increases doesn't mean to get bigger. Increases means to go towards positive infinity. We got to be careful with our language on that. So I would prefer when describing slope, you say gets steeper, gets flatter. Now, here's the new skill. The new skill is, so this slope is changing. So there's no one slope of the line, but we can find what's called an instantaneous slope by drawing a tangent line at the point in question. So here we go. We're going to draw a tangent line to this point here, point 2, because that's what I'm being asked to find. Remember from math that your tangent line is a line that touches the graph at only one point. What's it called if it touches at 2 points? Hopefully you said a secant line. I'll just jot that down. So that in case you don't know how to spell it, secant. So to draw a tangent line, what I'm going to do is I'm going to take my straight edge and I'm going to put it so it's on the point in question. right? And then almost like my pen is a seesaw, or my pencil is a seesaw, I'm going to move it so that like this is not a good tangent line, because if you notice, it's very close to the trend here, but not to here. Same thing if I go too far that way. I want my tangent line to be kind of like equally above or equally away from the above and equally away from the below. So let me throw that in. I did it with pen just so it showed up nice. I would recommend you do it in pencil. So there you go. There's our tangent line that shows how that graph is changing at that point. So now it says to find that slope. Well, to find the slope now, I want to choose 2 points that are actually on the line to find that slope. I'm going to use the point of tangency because we know that's got to be on the line because I chose it that way. And then just find something that goes through the grid lines nice. Oh look, this goes through the grid lines nice here pretty well, so I'm just going to use those 2 points. But now remember, your tangent line is going to be different than my tangent line because it's an estimation. And it's fine that it's an estimation. You use your values, I'll use mine. So here we go, I'm going to calculate the slope. That point for me is, what's that, 6? It's 30 meters minus, we know this is 12 meters. All divided by, and I've got 3.5 seconds minus 1 second, which gives me 18 meters divided by 2.5 seconds. All right, and what's that? Let's get that down into a nice number. So I should have grabbed my calculator, folks, before I did this, but I did not. So this is 7.2 meters per second. Let me just quickly do that off to the side. Boom, 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 boom. Okay. Yeah. So that's 7. Then this is 17. Boom. And 50. Yeah, 7.2. Okay, cool. And notice the units there, meters per second. All right. So let's go to the next page. What do the units of your slope suggest is the physical quantity for that slope? Meters per second. What do we know is measured in meters per second? Oh, I know. Speed. Speed is measured in meters per second. So this slope has to do something about speed because the units will always line up if you're doing stuff like that. Right? Whatever the slope of your unit, the units of your slope are, tells you something about the nature of it. Now, that might not be the speed. We'll talk about that in a later lesson, but it has to do with speed. All right, so finding the slope of a tangent line and drawing tangents and approximation, skill number 1. Skill number 2 is something called straightening the curve or the linearization of a trend. Now, I have all this information here. Feel free to read it. I'm going to talk through it. The idea here is, notice here we took a guess. We said that distance is proportional to time squared. But how do we know it was squared? The graph of the cube graph does that, kind of looks the same. The x to the 4th graph looks like that as well. There's a lot of graphs that actually have that shape. And we just took a guess at this. And so with this process that we're about to talk about, this linearization or straightening the curve process, takes the guesswork out and allows us to say exactly what the relationship is. It also lets us find what this constant is. And so we're going to engage in this practice. So that's what the purpose of all this text is, just to walk you through the notion about what we're using this process for, to find the exact equation of a set of data. Because that's what we do in experimentation. You don't just plot the data, you come up with a formula at the end of it so that you can then test that formula to see how good your formula is. So we're going to use this set of data to find the exact relationship. Then we're going to do it for another example from the previous packet. So the first thing in this process that we're going to do is we're going to plot the points. Oh my God, look, we've already done it. Yay, we plotted the points. Next, we're going to guess the relationship from our knowledge of what these relationships look like. right? Like how did we know this was d was directly proportional to t squared? Because we recognize that parabolic shape, right? That's what we're going to do. It's a guess, only a guess, but we're going to be able to confirm our guess. So guess, as I said, we've written in d equals kt squared for the guess of the equation, or d is directly proportional to t squared. But what does that mean? D is directly proportional to t squared. Well, normally when we say y is directly proportional to x, we end up with a graph that looks like that, where y is directly proportional to x. But what this is saying is d is directly proportional to t squared. That suggests then, if I plot distance here, and not time, but time squared here, I should end up with a linear graph. Y is directly proportional to x, d is directly proportional to t squared. Kind of weird, but there it is. So that's this process. We're going to take our guess and we're going to transform what's on the horizontal axis into what our guess is, and then replot the data to see if we're right. So in this case, what are we going to do? Well, I'm going to need to, from that original thing, I had distance versus time, I'm going to make it distance versus time squared. So I need a new column of data that has me do time squared. So by the way, that's what all of this text says to do. By the way, another example. If I guessed y was directly proportional to 1 over x, right? That's our inverse graph when we see that, y and x. But if y is directly proportional to 1 over x, if I plot y and 1 over x here, I should get a straight line. But there you go. So what are we going to do? We're going to create a new data column. Here, our data column says, from our previous example, since we know distance is directly proportional to time squared, the data column is going to be called time squared. Now, what are time squared going to be measured in? Well, time was measured in seconds, so time squared is measured in seconds squared. And so I'm going to take all my time data and square it. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. If you can't tell, I kind of cooked the data. So now what we're going to do is we're going to plot not distance versus time, but we're going to make a distance versus time squared graph. So here, I'm going to put distance, and I want to keep the same organization, right? We went up by 3s here, so 12, 24, 36, 48. But here, I'm not going to have time, I'm going to have time squared in seconds squared. So there's 16 across. Oh my God, convenient here. So I'm just going to go up by 1s, but I'm not going to write in all the things because that's annoying. And so then what you're going to do is you're going to plot this data. So take a moment and plot your data. And that's what it should look like. Oh my God. Look, we got a straight line. Hold on a second. Apparently the UPS guy is here. So that is what we were looking for. If we had guessed wrong, folks, if this was supposed to be a cubic graph, these points would not line up as a straight line. They would line up as a curve still. So what I'm going to do here is I'm going to take my straight edge and draw in my best fit line. So here we go. Boom. There we have it. All right. So if I guessed wrong, what I have to do, unfortunately, is start the process over, take another guess, make a new column, plot more data, and see if I get a straight line. You got to keep going till you get a straight line. And so next, what do I do? Well, we said, well, first off, what have we confirmed? We confirmed that distance is directly proportional to time squared. That is a correct guess because the distance versus time squared graph came out linear. So next what we're going to do is find the units of the constant of proportionality, its value, y, because if we think y is equal to mx plus b, and m is the slope, and I put this in that form, distance is equal to slope t squared, because t is what's on the horizontal axis, the slope of this line is our k. So there we go. Let's find that. K equals the slope of the straightened line. And so let's do that here. And I've got 48 meters minus 0 meters over 16 seconds squared, because I'm going to choose this point and that point, minus 0 seconds squared. And what do I get? I get 3 meters per second squared. Awesome. And so now our last step is to write the final equation. So take a second and see if you can figure out what the final equation is. All right. Hopefully what you did is you just took our general form. Distance is equal to, you take your slope, put it in parentheses, 3 meters per second squared times squared, and then you're done. Okay, and box it. That's our final answer. Well done, everyone. All right, that's the process. So let's try it one more time with another sample. And so, here's our sample. Graph D from our previous packet. So just to remind you of what that looks like, graph D from the previous packet was the frequency, wavelength versus frequency. You did that for homework, you got corrections on it. This is what it should look like. It looks like that hyperbola. So let's do this process to find the exact relationship between wavelength and frequency. So here we go. The first step is to take a guess. If I look at this, it looks like wavelength is directly proportional to 1 over frequency. So I'll just use the F for frequency so I don't have to write it out. Now, how do I know that's not inverse square? I don't, but remember, I'm taking a guess. If I guess wrong, my graph won't come out linear. If I guess right, it will come out linear. All right, so I know that's a terrible thing, but when we get to do this on computer, guessing wrong doesn't have as significant of a consequence, so don't worry about it. So here we go. So what does that tell me about what I need to do here if wavelength is directly proportional to 1 over frequency? Well, that means I need a 1 over frequency column, and 1 over frequency would then be measured in 1 over hertz. All right, perfect. So 1 over hertz. And we'll tell you more about a hertz later. So what is the title of our graph then? Well, we know that 1 over frequency is going to be measured in 1 over hertz here, and that wavelength is going to be on the vertical. And so wavelength in meters, I'm going to switch to pencil. Actually, let me just do the title, and then I'm going to switch to pencil. So wavelength versus 1 over frequency. All right, cool. And so now what you want to do is we need to generate our values. Now it's very tempting here, folks, to put in like 1 over 10, 1 over 20. But I can't do that because 1 over 10 and 1 over 20, 1 over 30, 1 over 40, 1 over 50, those aren't evenly spaced. I need everything in decimals. So let's do this. 1 over 10 is 0.1, 1 over 20 is 1/20th is 0.05, 1 over 30 is 0.033, repeating, but let's just call it a day there. 1 over 40 is 0.025, and 1 over 50, 1 over 0.020. I'll just make them all same sig figs just for the sake of argument here. Okay, there's our data. So why don't you take a second, stop the video, and plot your graph. All right, you're back with me, and that means that this is what you plotted. Notice those same values there. These things have magically gone from red to pencil because I was working in pencil with the ones I did before. So here we go. We can now just, you notice I got a straight line. Thank God it wasn't inverse squared. I don't have to redo it. Oh, thank God. Okay, anyway, so let's put in our best fit line. And this best fit line, notice, boom, there you go. So what I need now to do to finish it off is to find the slope of this. So the slope is going to be delta y over delta x. I picked some nice points here. I'll just pick the data points because I actually conveniently went through these two data points. Oh, I wonder why. It's because I cooked the graph, folks. I would never get results this nice if I were to do them for real. So I've got 80 meters minus 40 meters all over. That's 0.1, 1 over hertz. And then this is, what is that? Oh, 0.05, 1 over hertz. Oh, by the way, a hertz, just so that we don't have to deal with, not that you would have to do this, we would do this, I wouldn't expect you to know this, but just to make it easier, a hertz is a 1 over second. That means a 1 over hertz is equal to a second. That makes this next step pretty easy because I'm going to get 40 meters over 0.05 seconds. And there you go. Apparently that's 800. I think that's right. Yep, 800. And then, because this is 1/20th, 40 over 1/20th is 800 meters per second. Awesome. Oh, meters per second. That's speed. Apparently, wow, this slope has something to do with speed. We'll find out later that that's exactly right. So let's make our equation then. Wavelength is equal to, or rather is proportional to 1 over frequency. So that means is equal to k over frequency. And so k here is 800 meters per second. And then I put in the variable there, box it, and I have my equation. So there you go, a walk through the process, 2 samples of the process. Guess what your homework is? Not that one. Boom, you have one yourself. Once again, I will tell you, I didn't describe the experiment there, but this is your independent data, that is your dependent data. I did an experiment where I chose various masses for something and then timed something that happened when I changed the masses so that there's no lack of clarity, independent, dependent. And so this is your homework for the weekend.